Jacqueline already introduced me, so thanks for that. I don't want to spend too much time on this, but below my picture there's my contact info. So if you have any questions about this presentation or anything else lube oil related, just shoot me an email or give me a phone call. I'll try to answer your questions. So here we go. So we start kind of at the basics. So what is a lubricant? Well, lubricant is made out of a base oil and additives. We all know that, right? Base oils produced from crude oil by the petroleum industry and then the petrochemical industry, and the chemical industries also produce base oils that are known as synthetics. And the additives are products of the chemical industry, and together they form a finished lubricant. So it's quite straightforward. Now in this presentation, I'm going to focus on lube oil, but because grease is also a lubricant, we're going to sort of jump back and forth between lube oils and greases a little bit. So the grease composition, there's actually three components. So in an oil, there is the oil and the additives, but in a grease, there is a third one, and it's the thickener, right? And you see that here. So there's an amazing amount of base oil in grease, like 70 to 90%, and that's held by the thickener. And you may have heard this comparison where they compare a sponge holding water to a thickener holding the base oil. And so there's that much oil in a grease. And then in addition to that, depending on what type of grease it is, there is 2 to 25% thickener. And then there's additives, anywhere from 0 to 10%, depending on what kind of grease it is and what the application is for. So that is how a grease is made up. To continue a little bit on thickener types and what kind of influence that has on the properties of a grease. The thickener is a key ingredient in a grease. And the structure, as it says here, is usually fibrous. But the fiber structure of thickeners varies. And like I said, it traps within it the base oil and the additives. And the thickener performs a number of functions, including what you see here at these bullet points. It gives the grease its shear thinning rheology, so the flow characteristics of the grease. The concentration of the thickener determines the stiffness or the penetration or the consistency of grease, which is measured in a cone penetration test. It determines the dropping point of the grease. So the dropping point of the grease is a high temperature whereby that grease is no longer capable of resisting it, and then the whole compound falls apart. The thickener also influences the water resistance of a grease, because certain greases, like calcium-based greases, are more water resistant than others, right? It determines how shear stable the grease will be under prolonged working conditions, and how, as it thins out, some greases thin out when in its operation, and how that returns to its original consistency after the machine is being stopped, let's say. It influences the pumpability of a grease, and that is very important for centralized grease systems, especially at low temperatures, because you need a thin grease for a centralized lubrication system to be pumped, right? Sometimes that's referred to as the mobility of a grease. It affects long-term oxidative stability, and it contributes to the overall lubrication of a grease. And I wanted to mention this because you can see how of an important role a thickener has as a component of a grease. Now we go back to additives in general. So there is an array of additives available to formulators, many different kinds. And these types are available because over time, like they've been developed to solve interrelated problems. So interrelated problems means problems between the additives themselves. One product or one additive kind of hindering the performance of another additive. And they've also been developed to solve interacting problems between the base oil and the additive. And that is known as a balance within the formulation. So the formulators, they strive to design a recipe, if you will, which is very balanced. And then they talk about synergistic behavior between the additives. So the additives should not fight with each other. They have to support each other. And a synergistic behavior between the base oil and the additives. That balance within the formulation is the main reason why aftermarket additives are not recommended by us as an oil manufacturer. And I'm not saying that aftermarket additives are not good, because there are some high quality products on the market. But I'll tell you in the next slide why those should not be used. Still okay, Ralph?
Yes, it is.
Okay. So here, additives at work. This is a depiction of a metal surface inside a piece of equipment, can be anything, and a lube oil film. And within that system, some additives work in the oil and some additives work on the metal surface, so they are surface active. So you see the examples of that over here. Now, we're going into the separate ones in the next couple of slides, really in detail. But I wanted to use this slide to explain to you why aftermarket additives are not recommended. Let's say that somebody buys an anti-wear additive compound to add to their finished lube oil formulation. That will improve the wear protection of the product. However, you put too much anti-wear in there will no longer be placed on the metal surface, for instance, for a detergent. And if we talk about an engine, then in that case, the engine can become really dirty inside, because now the detergent doesn't work anymore. You know, this is a sort of a simplification of explaining it, but it's all related to the polarity of the molecules that try to find a place on the metal surface. If certain compounds are more polar than others, they will win that battle for a place on the metal surface, and the others have no chance anymore. So then there is no detergent, or the other way around. You know, then there's a lot of detergent, but there's no longer enough anti-wear, and then you get a wear problem inside the engine. But that's why we say aftermarket additives are not recommended in a finished formulation. So it's a very delicate balance. So additives, they enhance the base oil properties. They add properties to the base oil, which the base oil doesn't have itself. And by doing that, it enables the base oil to perform beyond its limits. And the general purpose is to protect the metal surfaces of the bearings, piston rings on liners, you know, gear teeth, whatever it is. Improve the lubricant performance, and some additives are used to extend the lubricant service life. And here is a table that shows an overview of the additives as they are categorized in surface protectors, lubricant protectors, and lubricant enhancers. And we will go into most of these in detail during the presentation. I just wanted to pick out some, you know, some that we probably see the most. Like a detergent in an engine oil is there to maintain cleanliness, but also to neutralize acids that are formed during combustion. And that is surface active, but it always works hand in hand with the dispersant. We'll come to that later. The anti-wear, as you see it here, as the word says, it is there to protect equipment from wear. But you can see that it's also a lubricant protector, because the anti-wear also acts as an antioxidant. And then there are lubricant enhancers like viscosity index improvers. Those are molecules that are used to make a multi-grade oil. And tackifier is an additive that is used a lot in grease. And you know, the word kind of speaks for itself. It makes that grease more tacky, sticky, adheres to metal surfaces better that way, makes it more resistant to water wash out, water spray off, that kind of thing. Well, like I said, in the presentation, we'll go over all of those. Here's another table that shows how much additives is in certain products. And again, we don't really have to go over all the separate ones because we'll do that afterwards. But as you can see, engine oils and automatic transmission fluids are very complicated formulations because they contain most additives, you know, like 10 components. On the opposite side, there are general, if you see that third column there, it's a general R&O oil, which is basically a turbine oil. A turbine oil contains very little additive. You know, so there's a big difference between the treat rate with additives and the type of additives that are being used. And that is not done by accident, because you could say, well, you put more additive in, it becomes better, but it doesn't work that way. Because actually some oils are better off with less additive than others. Like a general R&O oil, a turbine oil, should have the least amount of additives as possible because it prevents formation of sludge in an operating turbine. So that's one example of that. So if more isn't better, how much is enough? 1% additive treat rate in a turbine oil and 25% in an ATF. You see how widespread that is, right? And it's done for a reason. Now, let's talk for a minute about viscosity. We all know viscosity sitting here, you know, that's kind of very basic. So viscosity is the most important property of a lube oil. And what is it? Measurement of thickness or resistance to flow. You all know that viscosity gets thicker when the oil cools down and gets thinner when it gets hotter. But the reason why I say this is because now we're going to have a look at viscosity index improvers. We're going to have a look at how viscosity index improvers influence viscosity in relation to temperature. And with that, looking at how a multigrade oil is formulated. Viscosity is always measured at a certain temperature. So for industrial oils at 40 degrees C, you probably all know that, like ISO VG 32, ISO VG 46, those 32 and those 46 centistokes at 40 degrees C, right? But if we look at automotive engine oils, according to SAE, they are specified at 100 degrees C. And that is kind of something to keep in mind when we go through the next slides. Viscosity index. So here on this graph, we show the viscosity temperature relationship between a monograde oil, which is the red line, and a multigrade oil, which is the gray line. And it shows the viscosity change with temperature. So as you can see, when looking at the monograde oil, as it cools down, it starts to get really thick. But when it heats up, it becomes really thin. And that is not something that is desirable, because you want to have a viscosity temperature relation that is quite flat, to give that particular oil a wider operating temperature range. And that is what the multigrade oil does, because it becomes clear here from this graph that as it cools down that way, the viscosity is lower, and as it warms up, it doesn't thin out as much, right? You've got to keep in mind that the viscosity is directly related to the lube oil film thickness inside a bearing or in between a piston ring and a liner. And that is why we want to keep this from dropping too much, because then the lube oil film becomes too thin and metal to metal contact starts. Now, taking it to a little bit more of a specific level, let's have a look at a 10W30 engine oil. We already know that the viscosity changes with temperature, and the function of the viscosity index improver is to reduce the change in viscosity as a result of the temperature change. This 10W30 oil is made up of a 10W base oil with added VI improver or viscosity index improvers. And as I said before, we're looking at an engine oil over here, so it's the viscosity is specified at 100 degrees C according to SAE. And so this 10W30 oil, multigrade, is an SAE30 oil, right? But it's a multigrade, it's not a monograde. So being an SAE30, it has to have the same viscosity as the monograde SAE30 at 100 degrees C. And as you can see, it does. So it's a 30. But if we go to the low temperature side of the graph here, you'll see that it doesn't thicken up as much as the SAE30 does. It stays thinner, which is good for low temperature startup, because if the oil is too thick, it takes some time for it to be pumped to the top of the engine to lubricate the camshafts or whatever, valve followers or whatever is there. And so the 10W30 is better at doing that. And at the high temperature end, we want to make sure that the lube oil film thickness inside the bearings is thick enough to form that lube oil film that is thick enough. So we don't want to drop to this value of the 10W oil. Okay, so this is the sort of the result of adding viscosity index improvers. But how does that actually work? So viscosity index improvers are molecules that are designed to reduce the rate of change of viscosity with temperature. So they allow an oil to be fluid at low temperatures and maintain thickness at high temperatures. They are molecules that have the ability to contract and expand, as you can see on this picture here. So when it's cold, they sort of ball up into a very small size. And when it's warm, they expand and they become bigger. The size of a molecule is of direct influence on the viscosity of an oil. So by doing this, going from here to there or vice versa, it reduces the change of viscosity with a change in temperature. Is that kind of clear the way I explained it? So that's what it does. And here you can see that depicted in another way. So the VI, it's a polymer. It contracts when it's cold. So by doing that, it doesn't thicken up as much as the monograde. And when it heats up, it expands and it doesn't thin out as much as the monograde. So that's how that works. Now, earlier on, before the dinner, some of us enjoyed like a beverage. So my question to you is, how would that work with beer? I usually ask water, but I mean, here we can talk about beer. So how do you think that works? If you'd look at this, how would a beer react or water? Any idea? No, it doesn't, just by itself.
Oh.
We're not talking about freezing or boiling.
Oh, okay.
We're talking like in between.
Oh.
It doesn't change.
Yeah, you're right. It doesn't change. This is what it is. Right? Very low viscosity like water, and it just has a flat line. And when you talk about VI, because you look at typical data of lube oils and it's got a certain VI, a fluid like this has an extremely high VI. A fluid like this, with this large change, has a low VI, around 100. And those multi-grade oils have a VI of around 150. You know, so this is kind of an example of what happens here. And there are hydraulic oils on the market that have a VI of around 400. So they have a very small rate of change with a change in temperature.
The taste will change.
Hey?
The taste will change. Yeah, sure.
Yeah, if you put that in, yeah, this is not nice anymore. All right, so those were viscosity index improvements. And you know, if you have questions, just go ahead. You don't have to wait till the end. So now we're going to have a look at oil life. And oil life is very often limited by oxidation. And that's why an oil has to have an oxidative stability. And the oxidative stability is the resistance of the oil against oxidation. And oxidation is a chemical chain reaction whereby sludge, varnish, gums, acids are being formed. Viscosity goes up after a while, and it reduces the life of the oil. Now, if we have a look at, or let me put it this way, oxidation affects different types of lubricants differently, depending on the group of the base oil. So a group 1 base oil, just because of the way it is manufactured, the process of refining it is not capable of is only capable of taking out a limited amount of impurities in a group 1. But then you would say, well, that's negative, and it is, but there's also a positive side to it, because some of these impurities, they contain the natural oxidation inhibitors that are present in a group 1 base oil. So that gives a group 1 base oil a fairly decent oxidative stability, but not as good as a finished lubricant that is made of a group 2 base oil. Because of the manufacturing process of a group 2 base oil, the process is capable of removing more of those impurities. By doing that, it will take out more of those natural occurring oxidation inhibitors. So, you know, negative. However, once it's additized with an antioxidant, a group 2 oil has a much better response to the antioxidant than a group 1 oil. And so if you compare the service lives of the two, a group 2 goes further. Right? And then when we talk about the synthetics, group 3 and group 4, in this case, not going to group 5, but they have excellent natural thermal and oxidative stability, which is then further enhanced by antioxidants. Just a rule of thumb that is very often used when we talk about oxidation, how it reduces the life of the oil. We say that every 10 degrees Celsius rise over 80 degrees C, sometimes 70 degrees C is used, but it will reduce the life of the oil. And I have to say, a mineral oil, because synthetics can react differently, the life of a mineral oil by about half. So you run mineral oil at 80 degrees C and it lasts 10,000 hours. That same oil in that same equipment will only last about 5,000 hours if the temperature goes up to 90 degrees C. So that's all part of oxidation, because oxidation is very much influenced by the temperature. So for that reason, the formulators, they add an antioxidant to the base oil. So what does it do? It prevents varnish, sludge, and acid formation, and it slows down the aging of the oil. It limits viscosity increase because over time, oxidation will cause the oil to become thicker, and it becomes dark, and it becomes smelly, but then it's in a far progressed state. And it does that by reacting more readily with oxygen out of the air than the base oil. Right? There's this chain reaction that involves peroxides, which sort of speed up in an accelerated pace, and once it starts oxidizing, it goes faster and faster. The antioxidant additive, because it sacrifices itself, it's consumed. And it requires replenishment by top-up You know, large systems sometimes we sweeten, and smaller systems oil changes. Right? The oil is at the end of its life in a small system. You're not going to sweeten it. You're going to change the oil. Now we're going to the chemical stuff. Be gentle, sir. So there's hindered phenols, aromatic amines, ZDDP, zinc dialkyl dithiophosphatase, and that is actually an anti-wear additive. But it also acts as a secondary antioxidant in formulations. And then there is BHT, butylated hydroxytoluene, but I think that there are more. I just don't know. An example that I would like to use is something that I found recently. Like, we're talking about turbine oils here. So historically, turbine oils were formulated with a dual antioxidant combination, which is called PANA. So it's a two-part antioxidant. The PANA stands for phenyl A naphthyl amine, and it contains a phenolic and an aminic compound. And the nice thing about that is that the aminic compound depletes slower because there is a regeneration process within that package going on, where the phenolic antioxidant sort of regenerates the aminic antioxidant. And that has always been thought to be the, you know, like the top of the turbine oil formulations to give that oil a long life. Now, modern turbine oils that are formulated with group 2 and group 3 oils, some of them, they only contain a one-part antioxidant, an aminic antioxidant only. And recent studies have shown that actually leads to a longer oil service life and has less tendency for sludge and varnish formation. And that kind of plays into one of these earlier slides that I showed, where the treat rate of additives in the turbine oil, it has to be as low as possible, because the formation of sludge and varnish inside a turbine is detrimental for that equipment. Right, so that is kind of more modern technology. Excuse me. And then there are other examples where, for instance, that is one of our heat transfer fluids. It's got a 3-part antioxidant in there. So you can imagine how important it becomes for that 3-part antioxidant package to have that synergistic behavior between those antioxidants. Right, so it's all about those synergistic effects. Okay, pour point. Very, very important, especially here in northern Canada in the wintertime. We want to make sure that we get customers oils that have low temperature fluidity. So then we look at the pour point. And the pour point is the lowest temperature at which the oil will still flow. Just before the pour point sets in at a certain temperature, we talk about the cloud point. And you can actually see that because the oil goes from a bright, transparent, although could be amber type color, to becoming somewhat hazy. And most oils are made with paraffinic base oils. And paraffinic base oils, depending on the production process, they contain a certain amount of paraffinic wax. And at low temperatures, that paraffinic wax starts to crystallize. And what it actually does is those crystals, they grow bigger, and they start sort of holding each other. So it becomes a web of crystals, and it eventually turns that oil into a solid. So the formulators, they use a pour point depressant polymer to reduce the lowest temperature at which an oil will pour. So that's pour point depressants, often known abbreviated as PPD. And what it does, it prevents those wax crystals from growing too large. Of course, there's a limit to that, but that's how how that works. Now, I guess you guys all know what PAOs are, group 4 base oils, polyalpha olefins. That is a man-made molecule, still a hydrocarbon, but there's no paraffinic wax in there. That's why those PAO products, you will often see them in products that have very low pour points, like -50, -60. Foam inhibitors. We get questions from customers where they say, oh, I've seen foam. And say, how much is it? Hard, get a picture, or it's sometimes hard to describe. But a little bit of foam on top of a layer of oil in the side glass is quite normal. But excessive foam can cause problems with oil circulation and the oil film. Circulation because it disturbs the bubbles, disturb the flow at the suction side of the pump because the pressure drops there. So those bubbles they can collapse or actually cause cavitation to happen at the suction side of the pump. And it causes problems with an oil film because, as you can imagine, a vapor bubble or an air bubble is not capable of carrying load. So it will not, it's not capable of preventing metal-to-metal contact. And when we think about hydraulic systems, where the hydraulic oil is used as a medium to transfer power in the form of pressure from a pump to a cylinder or whatever, or a motor, whatever is driven there, bubbles are compressible. So if there is too much vapor or air bubbles inside a hydraulic system, what it does, it just does this. It becomes like a how would you describe that? Like you say buffer? Spongy, yeah, spongy, and it doesn't work anymore. So that's why we have to keep the amount of foam low. So for that, a foam inhibitor is added to the oil, or an anti-foam, and it helps to dissipate the foam more rapidly. Those are large silicon polymer molecules. This is an example of it, polymethacrylate. And what it does, it promotes the combination of those small bubbles into larger bubbles. It reduces the surface tension of the oil, so those bubbles, they rise to the top and they break. The surface of those bubbles breaks, and that's how the foam is dissipated. This is one of the additives that is not dissolved in the lube oil. So it is suspended in the base oil, and that's why in Petro-Canada we say that the minimum filter rating is 3 micron absolute. Because if we go lower, there is a chance that part of the anti-foam package will be filtered out. The other thing I would like to say about foam is foam problems are very often confused with air release problems, because air release is something different, but it shows up kind of in the same way as a lot of foam. And so yeah, that's one thing. And what was the other thing? That's it, go to the next slide. Sorry. Demulsifiers and emulsifiers. So some oils will be formulated to demulsify, which means to readily separate from water, and other oils are formulated to emulsify, so to make an emulsion. An example of an oil that demulsifies is an industrial gear oil. In an industrial gear oil, we want to make sure that any water that gets in there readily separates from the oil, and then because of the density being higher as that of the oil, the water will sink to the bottom of the gearbox, settle out, and then the end user or the operators, mechanics, they can drain off that water from the bottom of the gearbox. So the demulsifier, it lowers the water-oil interfacial tension, which promotes water droplet agglomeration and water separation from the oil. And they are anionic alkoxylated alkyl phenyls. and copolymers of ethylene and propylene oxides. Now, emulsifiers, that is the opposite. So emulsifiers, the formulation purposely aims to create an emulsion. And it does that by reducing the surface tension of the water to enable two immiscible fluids to mix. So the water and the oil will then mix to form an emulsion. And an example of that is a natural gas compressor cylinder oil, especially an oil that is there for sour wet gas, because a lot of natural gases contain a lot of water, and you need an oil that is capable of doing that in case that compressor gets shut down and that gas, which contains sour components and water, will now start to come into contact with the cylinder liner and cause corrosion. But if there is an emulsion of the oil and water in the gas in between, that emulsion contains the additives in the of the lube oil, like in this case the neutralizing additives, it's capable of neutralizing those acidic compounds and preventing corrosion of that cylinder line. Now, rust and corrosion inhibitors are other additives that are used. So to prevent rust formation, which is an acid or water attack resulting in the oxidation of ferrous metals, or corrosion, which is an acid attack of any metal with or without air. So the formulators, they add rust and corrosion inhibitors in their oils. What it does is it forms a protective coating on metal surfaces, and others neutralize corrosive contaminants. And the chemistries that are used are aminoborates and aminocarboxylates. And then there are tests that actually make use of those kind of rods, you know, like metal rods. And so the oil is, they're submerged in the oil, and then after a certain period of time, if it shows up like this, it's not good. It doesn't offer enough protection. Anti-wear. So what anti-wear does, as the word says, it minimizes wear caused by metal-to-metal contact. And it functions when the load, the pressure, and the temperature are high enough to activate the additives. But this happens at a lower activation temperature than EP additives. So anti-wear is like step one, and then if an oil is formulated with EP, that offers more protection. Now, this is actually really interesting because the ZDDP was invented during the Second World War. And it still is the most common, and I think the better working anti-wear additive on the market. So you can see how many years ago it was, 1944. It forms iron sulfides and iron phosphates on the metal surfaces as protective layers, and it also acts as a secondary antioxidant. Now, in more recent years, in heavy-duty diesel engine oils from a lube oil manufacturer in the US, they've introduced a product that contains a titanium compound. You know that?
Yeah, that would be awesome.
Oh, you? Philips?
Yeah.
Oh, yeah, yes. And you know, and I don't. Then maybe you could tell us. I haven't seen much of it. So what's going on?
You know, it's funny because even when, you know, we go down and we talk to the technical folks down there, I'm not entirely sure they have a good grasp on what's going on. Only that it works. So
Okay.
I don't have a technical answer for you on how or why, and there's only kind of a few real specific places within a diesel engine where they say that it works, or in certain engine designs where they find that titanium provides added benefit.
Okay.
Like they used to talk about it, especially too with like old flat tap design engines, that kind of thing, right? Where it would provide an extra layer of protection.
Yeah, that's where with ZDP you would increase the treat rate.
That's right. Yeah, and they always use it in combination with oils containing ZDDP too,
Okay.
right? It's in the presence of, it's in addition to. There's still, say, in most of our mainline oils, there's still 1,200 parts minimum ZDDP plus the liquid titanium additives.
Okay, interesting.
Yeah.
I think
Well-
Shell uses it too, don't they, in some of their oils?
I don't know.
Castrol was the other big one.
Castrol, I've seen it in like gasoline.
Yeah,
I know
Yeah.
it's one of the- or Pennzoil, whatever it was, yeah.
Well, you know, it seems because this one ZDP's been there since 1944, so it's about time that there's something different on the market, right?
And titanium just grabs your attention.
It does, yeah.
It's quite
Yeah.
sexy.
Yeah, yeah.
Our oil's got
Even
titanium.
the label of the bottle.
It's very sexy.
Yeah.
Yeah. Yeah, you know,
They
just
changed it.
one thing I would like to mention about ZDDP, a lot of, you hear a lot about, when people talk about anti-wear, talk about zinc, right? They all say, oh yeah, zinc, you know, I need more zinc. It's actually, zinc is not the active ingredient in the compound that provides the anti-wear. It's the sulfurs and the phosphorus. What I heard from chemists, which I'm not, but zinc is there to stabilize the compound. Is that right, Sarah?
Yeah.
Okay. Gear oils are sometimes formulated with an anti-wear additive based on boron. And it works, but in contact with moisture, it is sometimes a bit of a problem because the boron compounds, they form, in contact with moisture, they form boron salts, which will drop out of solution and they are corrosive. They're insoluble, and so then you will actually, contrary to a lot of other elements that are found by ICP, you know, like, I mean, it's really difficult to tell whether an anti-wear additive is still active by looking at the zinc and the phosphorus content, you know, same with calcium, because the element will always be there. But what I've seen is that in those gear oils that contain the boron, if there is a little bit of water contamination, you actually see the boron disappear. Natural gas reciprocating in the cylinders, phosphorus is used as the anti-wear compound. Natural gas screw compressors, phosphorus as anti-wear and corrosion inhibitor. And then silicon as the anti-foam and the corrosion inhibitor. ZDDP is not used because seen as overkill for low boundary lubrication. And a risk of ash deposits because try to keep this as clean as possible. Air compressor fluids use sulfur and phosphorus compounds. And it's all kind of based on chemical reaction with metal surfaces that form protective films. Extreme pressure, or EP. So most common are the sulfur phosphorus compounds, which are chemically reactive with metals. And then there are products, I think Chevron has one, a gear oil, that contains potassium borate. They're chemically non-reactive, they deposit a film. And then in the past, a lot of chlorine was used. But chlorine is nowadays is not used anymore because it's environmentally unfriendly or sensitive. So we don't use that. So how that works, it is activated by heat that is generated at the points of metal to metal contact. And that's where these form these protective layers under that pressure and that heat. Heat generated by rolling and sliding action or sliding only. And it forms a sacrificial layer between the metal surfaces and reduces friction that way. It happens at really high temperatures, above 180 degrees C, but that is in the lube oil film. So it's got nothing to do with the lube oil temperature in the bath or so, even not the lube oil temperature as it goes through the bearings. It's in the film. And the contact temperature must reach that activation temperature because if it doesn't work. And for that, there are solid lubricants that can be used, like molybdenum disulfide, graphite, tungsten disulfide. But those are difficult. They can't be dissolved in the base oil. So in greases it works better, but not so much in lube oil, or not as well as in grease. So sulfur phosphorus compounds are the most common, but they can be chemically reactive, so they can cause yellow metal corrosion. And that's why in equipment that contains yellow metal like bronze, brass, copper-based. We try to stay away from EP additives. The temperature limit of the product itself is about 95 degrees C. First of all, if it gets that hot, there will be a lot of yellow metal corrosion, but it's also the point where a mineral-based gear oil starts to fall apart. It just cannot handle that temperature. It's not for worm gear sets because that is a combination of steel and bronze, and it's incompatible with ZDDP. There is another way of formulating gear oils. And then we look more at an old-fashioned way of formulating gear oils mainly for worm gears, for the steel on bronze gear sets. And that is called compounding. And compounding is the addition of, in the old days, lard oil, tallow, to increase the polarity of the lube oil. And with increasing the polarity, the intent is then that the polar compound will stick to the metal better and it forms a much stronger lube oil film. Nowadays, that is synthesized. So there are still compounded products on the market, but it's not the animal fat that goes in there anymore. It's a synthesized product. So the fatty compounds, like the synthesized animal products, they have a polar nature, and the polar group attaches to the metal, and it forms a molecular layer that is really thicker and stronger. So it increases lubricity and reduces friction that way. Applications are for worm gears, steel on bronze, sliding action, and steam cylinders. Because the steam cylinders, they're not a lot around anymore, but because there is so much water and at high temperature there, you want to make sure that you end up with a lube oil film on the cylinder wall that has a lot of resistance against getting washed off by steam and water at high temperature. The downside of these compounded gear oils is the pour point. Because here in Canada, it's very uncommon to use compounded gear oils because we're looking at a pour point of -3 degrees Celsius. So just doesn't work, right? Especially not outside. But there is something else that has been formulated for that, and that is this. Gear oils with a mild EP additive. So instead of an industrial EP additive based on sulfur phosphorus compounds, there's a mild EP gear oil, which is a blend of ashless amine phosphates. And you'll see those products in multifunctional products. A very common one is Mobile SHC 600 series. Like in the Petro-Canada line, Synduro SHB, it's kind of the same thing. Those are mild EP gear oils that offer a decent EP protection without the yellow metal corrosion. They are often used in PAO base oils, and as such, so not having the problem of yellow metal corrosion and having the PAO, which forms a very strong lube oil film, it can be used in worm gears. And when you look at the gear protection that it offers, it's a little bit lower than in the industrial gear oil. So here, this picture here shows a laboratory test where gear oils are tested in a gear set. What they do is they measure the failure load stage. So that is the stage where the oil is no longer capable of preventing metal-to-metal contact between those two gear flanks of those two gears, as you can see them over here. And then in the industrial EP protection, the failure load stage is above 12. So some of these oils have the capability to still protect that gear set when the load is at, well, the 12 is just a number. What they do is they just hold one of the shafts, to put more load on the driving gear. And mild EP protection goes up to about a failure load stage of 12. That's the difference between the two. So these oils are not suitable for every gearbox, but they have their purpose. Now in Greece, make a little sidestep to grease, we always also use EP and anti-wear additives. And they are mostly solid lubricants that are also known as fillers. Graphite, molybdenum disulfide, boron nitride, tungsten disulfide. And these solid lubricants, they have the capability to protect from metal to metal contact under shock loading conditions and under conditions where there's a lot of vibration. Start-stop conditions, you know, where a lube oil film has not yet been established. Well, this particle size thing, that is according to an OEM specification. So here there's a, you know, an example of Caterpillar that is actually, I think this is used in mining shovels, where they use a lot of these fillers in the greases. Metal powders are also used, like for threaded connections, like drill pipe. Then we use aluminum, copper, that kind of thing, to prevent galling of the threads. And in a grease, it is more effective and easier to do as in a lube oil, because the thickener keeps the solid lubricant suspended. Now we were talking about greases, so we go to the next one, which is a tackifier in grease. So tackifiers are additives to improve adhesion and cohesion of greases and tackiness and stringiness. One of the things that, you know, that is actually laboratory test, but you can do that yourself too. You take, you put your fingers in grease, and then you kind of spread them out and look at how long that string becomes before it breaks. You know, and that gives you an idea of the tackiness of a grease and the way it adheres to metal surfaces. Very often gives you a good indication of the water resistance of a grease, because if it sticks to metal very well, it's very difficult to wash it off with water. And actually that type of performance is measured according to ASTM test by a water spray off test, a water washout test, and a forced string test. And like calcium greases are the most water resistant, and then the more modern ones like the calcium sulfonate carbonate type thickeners, they are really good at that. These tackifiers, they overlap somewhat with VI improvers, which are high viscosity base fluid components. But the negative impact of tackifiers on the grease, they have a negative impact on the low temperature properties of the grease. So the more tackifier that's in there, the less mobile a grease becomes. And, you know, so that becomes a bit of a challenge for a formulator, because if a formulator needs to formulate a grease that is really water resistant and that really sticks to metal very well, and he wants to use a tackifier there, then the minimum operating temperature of that grease is going to be not too low. You know, so with grease, it's always a compromise between water resistance, mobility, wear protection, you know, all these type of different things. Detergent and dispersant. So here we go back to engine oils. So the detergent and the dispersant, they work hand in hand. So we'll start by the detergent. So so first one thing to clarify. The name detergent could give you an impression, okay, you know, I'm going to use an oil with a lot of detergent and it's going to clean up my completely foul engine. It doesn't work like that. There are like high mileage oils on the market that contain a little bit more detergent and that have the capability for a little bit more cleaning. But the detergent in a lube oil is not like the detergent that you put on your hands and, you know, to wash the dirt off. The detergent is there to maintain cleanliness. So to start clean and prevent it from becoming dirt. That's the difference. So it prevents depositing of oxidation byproducts, wear debris, and dirt on metal surfaces. And it does so by forming a film that repels the sludge resin from sticking. And the other function of the detergent is that it neutralizes acids that are formed during combustion. And so here we talk about alkaline oils. And the easiest way to sort of identify that is by looking at typical data of an oil and see if that oil has a base number or not. So what is it? Calcium sulfonates, phenates, phenolates, and salicylates are all detergent type molecules. But the same ones are also made with magnesium. In the past, barium was used, but barium is now seen as an environmentally sensitive compound, so you don't see that much anymore. So these detergent molecules, as this drawing shows, they have a polar head, as it's called, and a hydrocarbon tail. Those are man-made in the chemical industry. The polar head, because of its polarity, wants to stick to the metal. The hydrocarbon tail is there to hold on to the oil, to the base oil. It's got to stay dissolved in the base oil, right? So what it does, this is a dirt particle, and it tries to push that dirt particle off the metal surface by just sort of surrounding it. And once that dirt particle is lifted into the oil flow above it, the dispersant takes over, and I'll show you that. So that dirt particle is now in the oil flow, and the dispersant, it keeps that, okay, we're talking about dirt, but here it says sludge and carbon, which is also contaminant, keeps it suspended in the oil, and doesn't, so that the oil can take it into the lube oil filters, so that contaminant particle to get filtered out. But it doesn't only do that, it also improves the separation of these particles, and it prevents those particles from growing together, because you can imagine that if they start to, as it says here, clump, they grow together, they become bigger and heavier, and they settle to the bottom of the crankcase, and it becomes a layer of sludge at the bottom of the crankcase. You know, this is not good, it becomes really dirty. It limits sludge formation. And it is a surface acting compound known as succinimides, polymeric detergent, and amine compounds. And these two cooperate to maintain engine cleanliness. And there is another drawing that I have here. I know they use, I didn't make this, I actually stole it. But so they use light blue, so it's a little bit hard to see those tails. But so the initial contaminants are here. They are polar, and they are attracted to metal parts. So they like to stick to the metal surfaces like bearings and whatever you have in equipment. Then the polar heads of the detergents are also attracted to the metal. And a good detergent, it displaces those initial contaminants with emphasis on initial. And it keeps those contaminants, and then the dispersant keeps those contaminants suspended by means of a particle charge transformation mechanism, as it's called. I didn't invent that, but so that is what it's called. Okay. Okay, the next one, friction modifiers. So here we're looking at automatic transmission fluids and passenger car motor oils. In one of the earliest slides, we've seen that an ATF is the most complicated formulation, right? Because it has 10 components or more. So you can imagine how important that synergy becomes between those different additives. So what that needs to do, it needs to lubricate, but also transfer power through selective friction in clutches and bands. And those clutches and bands in automatic transmissions are made of a lot of different materials. Carbon fiber, paper, sintered bronze, steel, you name it. So there are multiple friction materials in one automatic transmission. And that's what makes it so difficult. Because and each of those materials, they have a specific frictional profile. And the lube oil, the ATF has to be able to handle that. And the way it handles that is by optimizing the grip for each frictional interaction. A lot of clutches in an automatic transmission. And if it also optimizes that grip, it eliminates unwanted noises like grunt and growl, as it's known in automatic transmission. And the right grip ensures a smooth transitions between gears to prevent shudder. Last year I was involved in a field trial with a new product on city buses and with Elson transmissions. And then you hear all that stuff, you know, and then the people, you know, of course, you know, I'm not a specialist in automatic transmissions, but the people who work with them and who do the maintenance on them, they have a very good insight in those. And they can really tell whether the frictional properties of an oil will last. Because that's the thing. The frictional properties of the oil will have to last at a constant level. Because if it degrades, then this stuff happens. It starts to make noise. It starts to become uncomfortable for the passengers in the bus because it switches from one gear to the other and everybody goes like this, right? And that is what the automatic transmission fluid does. And that's why all these different materials and designs result in many different ATFs with their specific frictional properties. That's why there are so many different automatic transmission fluids on the market. Now, in recent years, I guess 10 years or so, multi-vehicle ATFs have been developed, right? And a lot of people think, oh, you know, it's a multi-vehicle ATF, and so I can use it in anything. Well, it doesn't work like that, because it is still a multi-vehicle automatic transmission fluid is still not suitable for just any type of transmission. Like we have two multi-vehicle transmission fluids in our product line, and the differences are not only the frictional properties but also the viscosity. Because nowadays you see designs that require very low viscosities because of fuel economy. Now, because there is so much different material, there are also a lot of different friction modifiers. And so I just thought to name them many different organic friction modifiers. They're non-metallic in nature, without mentioning what it is. I think this is the last one, a seal swell agent. So hydrocarbon base oils are non-polar in nature. PAOs are even more non-polar in nature. So these oils, the purer these oils become, the lower the polarity, and the more they will cause shrinkage and brittleness and hardening of certain elastomers that make up the shaft seals. So the formulators, they use seal swell agents to add to the base oil to ensure that those seals do not shrink, do not get hard, and that they can keep doing what they're supposed to do, like keeping the oil inside and not leaking outside. So there are components with high solvency, alkyl benzenes, dibasic esters, aromatic hydrocarbons, a lot of aromatic compounds that are in those seal swell agents. Yeah, and I think this concludes the presentation. Any questions? Ralph, any questions from your end?
No one's raising any hands.
Okay,
We're good, thank you.
I hope that means it was clear as mud.
Clear as mud.
I noted that you talked about the use of solid lubricants like moly or whatever, especially talked about their Additives in a grease type of formulation. But you do see it as an anywhere additive from time to time.
Yeah.
In a lubricant as well. I don't think that you guys
We don't have it.
necessarily do that.
No.
But what are your, do you have thoughts on that in terms of how well it works as an anywhere additive in a lube oil?
Yeah, well, I actually experimented with it myself, and I'm not claiming that that it would work anywhere, but my hobby is vintage motorbikes, and I had an English motorbike that where the gearbox was not meant to cope with the amount of power that it produced, because they kept increasing the engine displacement, and so it was a common problem for the gear of the first gear to start pitting and getting started welding and then break. So what I did was I put molybdenum disulfide from moly coat in there, and it worked amazing. The problem was gone. So it does work, but I'm not saying that I don't have the experience to say, well, it works in anything.
Yeah.
I don't really know.
Yeah, and that's a specific kind of shock load event that's occurring in that, right? So
Yeah, yeah.
that's interesting.
Yeah. So the examples that you have seen, what are those?
Well, natural gas engine oil.
Oh, like the HDEX.
Exactly.
molybdenum in it.
HVAC is where you see it.
Yeah, we don't use that. Well, if there are no more questions, then thank you very much for your attention.
Thanks, Ralph.
Thank you, Peter.
Thank you very much,
Thank
Peter.
Thank you, Jacqueline.
Thank you, everyone that's over on Ralph's side. If you do have questions after this, definitely feel free to contact Ralph or anyone on the STLE, and we will help you or direct you to Peter. We gave Peter a nice water bottle for a speaker gift for presenting for us, so thank you very much. I think I have the